It's 12 o'clock exactly, so let's make a start. Good morning, everybody. Just to say, it's a real pleasure to be able to welcome here to Tigme, to Marco Ellero from BCAM, from the Research Center in the Basque Country on Applied Mathematics, which is called BCAM. It's a real pleasure to have you here, Marco. Marco and I go quite a while back. In fact, Marco was a professor in Swansea University a number of years back when I was head of the College of Swansea University. But Marco has had quite a long and prestigious career in a number of places in Europe and in other continents. I know that Marco started in Berlin, but then moved on to Sydney, and then back to Madrid, and then to Munich, to TUM, and then to Swansea, and then now in BCAM. I think I got more or less more or less, with perhaps a little permutation, but more or less the order right. So Marco has been in a number of prestigious places across the world. Marco's expertise is in computational particle mechanics, and a very interesting part of particle mechanics, often working at the mesoscale, perhaps not at the atomistic scale, perhaps not at the continuum scale, which is what many of us are used in here, but very often working at the intermediate type of scales and working with geology and a number of other aspects of physical processes. And the talk today, I can see that it's attracted quite a lot of interest because it's based on the use of these technologies for the very, very important and critical application of coffee. Obviously, coffee keeps us all alive, keeps all the research centers working. Without coffee, probably there wouldn't be any research neither here in Sydney nor in many places in the world. So this is really a talk with a lot of impact in many aspects of society or many aspects of research. So really, thank you very much, Marco, for coming over to Sydney. We're trying to develop collaborations between Sydney and BCAM. BCAM is also at the Ochoa Center. Perhaps most of BCAM is a little bit more theoretical than we are, but Marco represents a more computational and perhaps a little bit more applied part of the BCAM. So it's great to have Marco here talking to a number of people in Sydney, and I'm sure that you will find this talk very, very useful and informative. So over to you.
Okay, good. So thank you very much for the introduction and also for the invitation to Sydney. It's a pleasure to be here and also to have had some discussion with other members of the center about different topics. We realize that there are many different interesting overlapping interests that we have, and had some very interesting discussion. And of course, to see again Javier after, I think, 7 or 8 years, I think, since we left Swansea in 2015. So it's a pleasure to meet you also in person. So, so in connection with this talk, what I'm going to discuss with you today is the results of a collaboration that we had over the past 2-3 years with an Italian brewing company, which is the Indica Cafe, which is originally from the northeast part of Italy, Trieste, where it originally come from, and also with Swansea University, as you will see during the talk. So the goal is a little bit to introduce you into the complexity of the physics and fluid mechanics that occur during a typical espresso extraction. And we try to also highlight the different challenges that there are in modeling and simulation, and describe also the link, the physical link between the changes that occur at the level of the microstructure of the coffee bed with alteration in the flow property, resistance of the bed, permeability, etc. I will mostly talk about theory and simulation, but I will also show you, we had a collaboration with Swansea University. They perform also experimental analysis of coffee bed before and after extraction using X-ray micro-CT. So that I will also show you some experimental results to support some of the results that we observed in that area. Okay, so just very quickly, one slide regarding our group in Beckham. So I'm in the CFD or computational microfluidics rheology lab. We are mostly interested in multi-scale fluid dynamics. We apply the core expertise that we have is on particle methods. We use essentially particle methods at different scales to solve flow problems at different scales. So we have SPH, smooth particle aerodynamics, or stochastic particle methods like DPD, the mesoscopic hydrodynamics problems, or also DEM, and we are also interested in the combination, the multi-scale coupling between all these different scales. We had some interesting discussion before this talk. And the general application that we have so can be classified under umbrella of complex fluids. So we're interested in non-Newtonian complex fluid mechanics, polymer melts, granular systems. We have a number of people in the groups that are involved in many of this, from hemodynamics to particle suspended non-Newtonian media, magnetic suspension. But today I will mostly focus on porous media flow, in particular porous media that can, they are deformable, they can morphologically change during a process, and how these morphological changes of a porous media affect flow properties. Okay, so I should also thank the collaborators. The main collaborators on these projects are, well, first the people that introduced me into the world of the coffee and the espresso extraction, which are Luciano Navarini, who is the head of the research department in Italy, and Furio Sugili Verani, who is the former CSO. Now he's retired just a few months ago. But as I said, I also will also have experimental data. So all the X-ray micro-CT analysis were performed in the Professor Johnston lab in Swansea University, and most of the simulation were performed by my postdoc Chao JMO, who was in Beckham, and now he moved back to China. Okay, good. So coffee. So we usually, as an introduction, correctly, we all know coffee, and we use to brew the coffee in many different ways. Everyone has his own favorite. You can filter, or maybe in the morning you wake up, you get the mocha or other things. Espresso is just one specific way, one patented way to brew coffee, which is just by percolating hot water at 90, 95 Celsius degree under very high pressure. So you have an espresso machine, essentially the overhead pressure could be 9-10 bars, so it's quite large, in a very, very short time. Okay, so we have so it's a short time, high pressure filtration. And the result is that you have a cup of coffee, which usually in Italy range between 20 milliliter called ristretto, or 50 milliliter lungo with a regular shot between 20 and 30. Okay? So this is more, it's different in other countries. Maybe the amount of is a little bit larger than the classical espresso. So why there is interest in the industry is everything is related to the desire to tailor specific flavor and aromas. And during the extraction of the espresso extraction, there are many different organic compounds which are extracted. And here I just show you a list of 10, but there are many thousands of compounds which are essentially related to different sensorial perception. For example, caffeine is related to bitterness. There are other compounds which are related to astringency, sweetness, and so on. So therefore, to understand the extraction kinetics of all these substances, it helps people in the company to target or profiling a specific cup of coffee, optimizing some property, or also differentiating the flavor. Okay, so you will see that tuning specific property, it allows you to extract more, or to balance towards more compounds with respect to another, and therefore differentiating and also meet the consumer desire. So this is a challenging problem to model, and there are many different reasons. One which is more structural, the other is related to the complex physical process that occur. From a structural point of view, the problem is fully multi-scale, and we know every time that we have to model a multi-scale problems, we have computational and numerical issues. The multi-scale nature in coffee comes from essentially, well, first of all, you have your powder, which makes your coffee, and the powder is typically, you have different sizes and grains, and almost all the powders have a final bimodal, or maybe in some cases trimodal distribution. So essentially, you have the largest particles, which is in red there, which correspond to typically 500, 400 microns. And then you have fragments, which represents the so-called fines. So the larger particles are in coffee jargon are called coarses, and the smallest particle, 40 micrometer, are the fines. There is a scale separation already 1 order of magnitude between the two. Then, of course, we have the organic components, which are the material that we want to extract, the molecules of caffeine, trigonolene, etc., etc. It's not only this. So if you look at these solid particles, the internal structure is not homogeneous, it's heterogeneous itself. In fact, the coffee is a plant. So there is a kind of level of porosity inside, which is represented by cell pockets, essentially cavity where originally the cells were contained, which have been destroyed during the roasting process. And all the nutrients, all the elements, all the properties that you want to extract are attached to the wall of this internal cavity. Okay? There is another important thing is that the walls of this cavity are also porous, and we talk about nanoporosity. And nanoporosity of the wall is important because it determines the level of water which will be absorbed by the solid phase. So during our typical extraction, water imbibes the entire coffee bed, then imbibes all the coffee grains, then it can imbibe also the wall. When you imbibe the wall, the amount of water inside the wall determines the level of stretching of the wall and therefore the swelling of the particle. And you will see that swelling of the particle is important because it will alter resistance and permeability of the coffee. So therefore, there are many properties. There are also complex physical processes that we take place during extraction. So the first interesting property that need to be addressed is transient permeability. So if you apply a constant pressure drop when you do your extractions, the first things that you observe is that the flow rate or the permeability reach a certain values, but then it does not stay there. There is a very slow relaxation time. Okay, so therefore you have a peak velocity and then gradually slow down up to values which are much smaller. If you stop the extraction there and you reactivate extraction in the same direction, the flow rate goes to the same level. If you now overturn the capsule and you redo the extraction now in a coffee bed which has been overturned, then again you get a maximum, a peak, and then a relaxation again. And this is an experiment that was done by Divarani and Petracco back in the 90s that is believed to be associated to a migration of the small fragment of the fine inside the matrix during the extraction process. So this is something that needs to be considered. Of course, coffee is a granular bed. We have grain packed together, so consolidation is the problem. But I will mostly focus on other two aspects, which are very important also, which is the swelling. Particles, coffee particles in the powder will be inhibited with water and they will eventually swell. And another things that can happen is that during extraction process, the particles are not rigid, but they can lose mass. So essentially, the size of the fines of the fragments that we observe in the granulometry analysis, they increase in time when you wet the system. Okay, so therefore, erosion of the surface of the particle is another important features. Okay, so there are a number of light reading for the people that might want to just have a first easy introduction to the fluid mechanics, thermodynamics of coffee. I will recommend, however, for example, the last one, who is an edited book, which although it's not specifically dedicated to coffee, there are 2 chapters edited, written by John Melrose, who specifically focus on coffee brewing and modeling issues. And this is a very nice 50-60 pages. There are 2 chapters that is quite interesting reading, live reading to get into these topics that I mentioned. Okay, so therefore this is what we want to model: fine migration, erosion, swelling, we'll use our expertise in particle method, in particular SPH, and so therefore we will use the smooth particle hydrodynamics method to address some of these issues. I will also, in the third part of the talk, I will show you also this experimental data on coffee bed. And Professor Johnston lab in Swansea, they have performed X-ray micro-CT analysis of a capsule containing a powder under dry condition and also after extraction to see how the morphology changes. And then finally, I will talk about swelling. And in the last part, I will talk about a one-dimensional model which can model extraction. Because of course, in the company, you cannot do SPH simulations. You will need very quick ways to look at extraction kinetics. And in particular, I will discuss about two different ways to drive the flow, which is one is the classical pressure-driven, which is normal in every coffee machine, and another one which is flow control, which you will see there are some interesting features. Okay, so fine migrations. So we use smooth particle hydrodynamics. I think that here in Sydney, many people are at least have heard about this, and of course we have Javier, who is a worldwide expert in SPH. I will not go into the details of the equations. We just solve an Navier-Stokes equation for the liquid phase. The most important thing that I want to clarify is how we handle the different scale that I mentioned before. So remember, we have the coarses, the largest particle, then we have the fines, the smallest fragments, and then we have essentially the organic compounds that we want to extract. So at the level of the coarse, we simply fully resolve so to say, we consider a model which resolves the hydrodynamics around the courses. In terms of the fines, we consider just a single particle model. One SPH particle will represent one small fragment. Now, if you just have one SPH particle, it does not produce any alteration to the flow because it's just a discretizing element. But as long as you fix one particle, it will produce an alteration of the flow around it. And therefore, one SPH particle, it can be interpreted as a spherical particle, solid particle, with a certain hydrodynamic radius, which is the order of the cathode radius in SPH, as long as you fix it. Okay? If it is free, there will be no effect. At the level of the concentration, since the organic compounds are order managers model, we just use a continuum approach. We have a concentration field, and we solve advection diffusion equation for this concentration field. The advection diffusion equation will be solved over the entire domain, the liquid and the solid phase inside the courses, in order to detect, so to say, the dynamics of the compounds from the solid phase when it is released in the liquid. In fact, we will use different diffusion coefficients, bulk diffusion coefficient, and also a different diffusion coefficient for the compounds inside the course. You have seen that inside the course you have a porous structure, so that for the same molecular compounds, when you want to capture the diffusive behavior inside the solid structure, will have a diffusive behavior much slower because the diffusion is hindered by confinement. The pore cells are the order of 40 micrometers, 30, 40 micrometers, so therefore at the same level of the fines, more or less in the side. So therefore there will be a very slow process taking place inside the solid, and then we have the bulk diffusion coefficient for the liquid, and we have a release coefficients with taking into account the unidirectional transfer of mass between the solid and the liquid. Of course, the physics of how compounds go from the solid enter the liquid is much more complex, but we decided to, in first approximation, to lump everything in a diffusive process, which is what also other people did. Okay, so the first thing we want to target is transient permeability, and here we have a minimal model of the filter. This is the model that we have. So we have our courses; they are fixed large particle, and then we have the fines, the small particle which move with the flow under the action of a gradient of pressures. And what we will see is that when fines reach an upper regions, which we call filter or buffer filter, then we stop them, we freeze them, and as long as we freeze them, they produce a resistance over the surrounding flow. So therefore, if you fix a 1 SPH particle, it will produce a drag, which is 6 pi eta, the radius of the SPH. as the filter accumulates fine during time, it will produce a resistance which is proportional to the resistance of single fine multiplied by the concentration of fines which are trapped into the filter. And this is concentration is time dependent because it will depend on time. In the typical time of extraction, 20-30 seconds, it will accumulate more or less. Okay, so therefore, this will be essentially the idea of the transient resistance. So we use a simple, in this initial work that we have done back in 2019, we use a simple 2D model. We reproduce the thickness of the coffee cake in the entire length, order of 1 or 2 centimeters, and then we try to reproduce also the right ratio between the thickness respect to the size of the courses and the ratio between the courses and the fines. And also we modulate the granular pressure to reproduce flow and a Reynolds number, which also reproduce the typical flow rates observed in extraction. And this is between 1 and 10, 0.1, or 1 and 10 in Reynolds number. So therefore, espresso extraction is also quite fast, although we are talking about a microfluidics. So if we have Reynolds number up to 10, which means that it's not creeping flow, it's not turbulent, but inertial flow effects could be important. So I will show you also later. Okay, so, well, first of all, with the presence of the fines, we were able to reproduce the transient permeability. We have applied the same setting that was discussed in experiments by Diverani and other people. We have, we activate a pressure drop, then we switch off, we reactivate the pressure drop in the same direction, then we switch it off, and then we invert the direction. And what we can see is that if there are no fines, essentially, the flow rate reaches the maximum level, goes to 0, to the maximum, there is no relaxation at all. If we introduce the fines, depending on the amount of fines that we introduce, we can essentially match the points. I don't know if you can see here, the points are the experimental data. We can essentially tune the concentration by and reproducing exactly this relaxation process. And essentially, the idea is that the fines need some time to move from the bulk or from one part of the filter to the other part of the filter. During this free flow, essentially, they don't oppose any resistance. It's just the viscous resistance of the solvent. But as long as they accumulate in the other regions, the resistance start to build up and eventually produce a long time process which describe the decay in the flow rate. Oops. Okay, so therefore we were able to reproduce this morphological let's say this change in the resistance related to the fines. Another thing that is important in company is to see how these fines affects the breathing profile, and the two quantities which are typically considered are so extraction yield and extraction strength in the coffee industry jargon. The first one is the ratio between the mass in the cup and made dimensionless by the initial mass of coffee in the coffee bag. Okay, so therefore this will tell you how much of a certain compound has been extracted. Okay, so one will be 100% has been extracted. The second has to do with the concentration in the cup. So the same mass is made dimensionless by the amount of liquid which end up in the cup. So therefore, there will be a time-dependent concentration of a given compound. So we can see that if we introduce the fines, which is the blue line here, compared to the no fines at all, we can see that the strength of the beverage changed quite significantly. In fact, with no fines, we have a small peak at short times, and if we increase the fines, we have a much larger peak, so increase of 200 or 300 times, and also the peak is shifted to the right. And this can be explained simply by the fact that obviously the resistance increase, the flow rate decrease, the time that spent on elements of liquid near the solid interface increase, and therefore the mass transfer between the solid and liquid increase as well, therefore increasing also the concentration in the beverage. So therefore, fines is one of the crucial aspects in all this powder because it allows to gives more strength to the beverage. We saw also the question inside the solid phase, and this is also quite important because this is the slowest process that takes place. It's not the diffusive process that takes place in the bulk, which is really relevant. In fact, the pecking are very good now. But it is the slow diffusive process of the compounds inside the liquids which determine, in the end, the extraction. So if you change for the typical brewing time of an espresso extraction, which is order of 20-30 seconds, you can see that by changing the diffusive coefficient of the solid by 4 times, you can end up with 2 very different scenarios. In one case, you can see that essentially material has been completely extracted. So we have red regions. This is completely fully extracted, while in other case, there is significant portion of the coffee bed which is not accurately extracted, and this is something that represents the problems also for the extraction, practical extraction. Another thing that we observed has been reported also in some recent literature is that you can have also uneven extraction profile, which means that, for example, if the flow rate is in this direction now, okay, so we extract it toward the upper part, you can see that region of the coffee bed which are near the inlet are much better extracted than region near the outlet, and this is of course related to the fact that here we have fresh water at 0 concentration, so the transfer of mass between the solid and the liquid is basically a gradient of concentration. So the gradient of concentration is the maximum, the mass transfer is maximum. Here the liquids come already almost saturated, and therefore it's not able, even if you slow down the time, it's not able to extract any material. So this kind of situation that can be present and has been reported. By using different diffusion coefficient, we can target experimental data in the ILI, so we can essentially reproduce the time-dependent yield extraction for different compounds just by tuning the S. And I would like just to stress here that one of the important property here that you have when you perform extraction is that, as you can see here, different substances are extracted at different time. So that for different compounds, for example, caffeine is extracted quite quickly, trigonal and other substances are extracted quite slowly, which means that since all these substances are related to a certain sensory perception, bitterness, acidity, etc., if you stop the extraction at different time, you will change the balance between these. Therefore, you will change also the flavor and possible aroma of the coffee. So therefore, the extraction time, 25, 15 seconds, or 30 seconds, is also one way to differentiate between different beverages. Okay, so that was regarding the fines. Why are important? Why they are included in the powder that are extracted, and we will go back to the fines later. And now I would like to discuss the process of erosion. So we have seen that from experimental data that when you wet, so if you have a dry powder, and if you look at the granulometry of a wet post-extraction powder, this peak in the granulometry corresponding to the fine increase in size, which means that you have more fines. So therefore, there are some fines which have been eroded that were not there. So therefore, this is a problem that needs to be addressed. In terms of erosion, there is a lot of work that has been done, especially sands, etc. So we have a model which are typically based on shear stresses. Essentially, you assume that the normal forces balance, and what is the critical force that produces the erosion is a kind of tangential force which can be associated to hydrodynamic stresses. And these are quite works quite well for wetted system. However, in the case of coffee, there are some reason for which this might not be the most appropriate model, just a simple shear erosion model. And the reason is that inside this coffee particle, these courses, there is some trapped air and trapped gases. And we know that there is some trapped air and trapped gases because during the extraction, these are eventually solubilized and they form the foam. Okay, so the foam that you get in your extraction is due to the internal air and CO2, which is contained into this form. This is a very, very slow degassing process. So after the roasting, these are producing the roasting. then they reduce, so to say, the amount, and then the final degassing process is very, very slow. At the moment where you extract the powder, there are still gases. So the fact that there is gas inside means that actually there is no complete balance between the pressure of the liquid outside and the pressure inside, because the liquid is not able to inhibit all the structure. You might have still, during the typical time of extraction, which is just 20 seconds, you may have a significant portion of this time where there is imbalance of the pressure at the surface. So therefore, a pressure-dependent erosion model might be more appropriate for these cases. We have developed this one bottom-up model for based on SPH, and this is in this work here. And the idea here is that it's a kind of bottom-up model. So we act. It's not a continuum model. We act at the level of the forces acting between the particles. So therefore, here we have a course. The course is made by many SPH particles. Some of them are located on the surface, and they are linked together with springs. Okay, so therefore, when some hydrodynamic forces try to drag the particle away, for example, from the other, they will produce a stretch in the springs. And when the stretch, which is what we call delta Li, if the stretch of the spring exceeds a certain critical level, then this particle will be eligible to be eroded. Okay, so therefore we can assign a probability to the particle, which is actually proportional to how much the spring stretch over the critical values, and then we use a stochastic method to produce a realization, whether it is broken or not. If a particle is eroded, then become a fluid particles, and some portion of the surface will be exposed to the fluid, so that we will redefine this blue surface particle, and the process will continue. One of the interesting property of this model is that if you plot the erosion rate in function of the normal and tangential forces that you act on each of the particles, then the process is heterogeneous. It does not depend only on the tangential forces, as typical occur with shear erosion model, but there is an influence also on the compressive forces, which means that the larger the compressive forces they have, the larger will be the tangential forces needed to produce erosion, because the compressive force is actually consolidated to the say the mass. The smaller the compressive forces, the easier will be for the tangential forces to reach a value where erosion is produced. Okay, so therefore there is a two-dimensional map here which show the effects of both normal and tangential forces. You can see better here where there is a kind of yield or failure criteria of the typical Moore-Coulomb type, where up to a certain value of the tangential force there is no erosion, and then if exceed some value, then it progresses linearly. And this yield value, this threshold value, actually depends on the value of the pressure. And the relation that we observe here is that we get this behavior between this threshold or threshold shear stress, where we have essentially sigma represent the compressive forces or the pressure, tangent of C represent obviously the angle of internal friction, which gives the slope of this curve, and C is the intercept with the zero compressive force, which give the cohesive particle. So therefore, we have a pressure-dependent erosion model, which depends also on the granular properties of the internal structure. So we can look at the flow pattern of the erosion with this model and see what are the effects. So we use some 200 grains, we apply the flow rate, and then we look how the patterns evolve. And you can see that essentially this is the mass, these are the velocity, the micro velocities. There is some channelization effects that occur, and there are some preferential channels with recruit mode of the liquids. There are erosion patterns that you can see, they are observed, but the most important thing here is that, which is never observed in shear rate erosion, is that there is an inhomogeneity or heterogeneities that develop in the direction of filtration. Okay? Usually, you always have heterogeneities in the transverse direction, which is called channelization, and which essentially is related to the shear forces. But here, due to this due to this, to the presence of the pressure in the failure criteria, you have an heterogeneity also in the filtration function. How can you explain this? There is more, the flow goes in this direction. Here there is more erosion. Here there is less erosion. At the inlet, the pressure, you have a pressure drop, obviously, that develops in your system because you have a flow. Okay? So therefore, at the inlet, the pressure is quite large. The local pressure increases the failure for the stress, and therefore you need very, very large shear stress to produce some erosion. Essentially, you will not erode the material alone. At the outlet, you have very, very small value of absolute pressure. We're not talking about gradients here, not pressure drop. This is just absolute value of the pressure. At the outlet will make this contribution smaller, and therefore it will be easier for the tangential force to be active and overpass the threshold, producing eventually erosion. The erosion is always take place by shear, but the threshold which determines whether and to what extent shear will have an effect depends on the pressure. We look also at how different parameter affects the patterns. For example, cohesion, the cohesive parameters promote channelization. Okay? However, in terms of the filtration directions, there is almost no effects. So the cohesive parameter does not produce any effects. This is the profile of the solid volume fraction in the y direction. So there is more mass at the top, less mass at the bottom, at the outlet. And you can see the C has no effect on this. What has really effect is the angle of internal friction. When the angle of internal friction is 0, the tau C, the stress, essentially will not depend on the pressure because you have sigma, the pressure multiplied by the angle of internal friction, so there will be no dependence. And we go back to a simple shear erosion model. In a shear erosion model, although you have sterilization, the transverse direction, you don't have inhomogeneities in the filtration direction, which show that essentially this mass profile is more or less constant, where if you increase the angle of internal friction, eventually you can get back to the situation direction. So therefore, the take-home message here is that we need to introduce a pressure-dependent erosion model. This introduces heterogeneity both in filtration and transverse direction. The first is determined by the angle of internal friction. The transverse direction is determined by the cohesive parameter in your constitutive models. And more importantly, we have this heterogeneous profile in the filtration direction, which develops only if the erosion is pressure dependent. If it is shear dependent, it will not be dependent. So why I'm saying that, I'm going back to some also some experimental measurements that we did using X-ray micro-CT by our colleagues in Swansea University. We are looking at images like that, where this is the typical capsule, Espresso capsule provided by the ILI, and we will look at different powders compressed in this capsule to analyze the distribution of mass, etc., before and after an extraction. Okay, so we try to infer something about what's going really in the system. The capsule, so the powder, we analyze 4 different powders. So one is the classical espresso, hyper espresso, H, refilling mocha, the powder that we typically use for the mocha extraction, and another one. And you can see there are differences in terms of the granulometries. For example, the size of the courses is slightly reduced in type M, H, and E. And also the percentage of fines is somehow changed. In some powder, there is more fines than the other. Okay? There are really different granulometries. And this is just give you an idea of the vertical cut. But of course, the X-ray micro-CT analysis provides full 3D information of the entire coffee batch. When we have the X-ray micro-CT data, we in principle have the geometries. Okay, but there are some issues, and now I would like just to have 1 minute to explain also some issue that we have when we try to binarize micro-CT data. So if you have a suspension of porous media where the solid phase is more or less homogeneous, it's not that difficult to distinguish what is voids from what is solid. However, in the case of coffee powder, this is not the case, because I told you earlier that even the solid particles, the courses, are not homogeneous. they are made by many different pores, which are actually the cell pocket. So you have many internal pores, which make the structures not fully solid. So therefore, how can you use X-ray micro-CT to determine, for example, the geometries from the coffee bed? We have different. We can essentially you have a threshold value which is a so-called grayscale threshold, which can allow you to tell what is solid and what is liquid, okay, from X-ray microscope. Essentially, you can go from full black to full white. Porosity is 0, porosity 1. Okay? So how to choose the right one? We don't know exactly, because in this system it's easy. So what we do is, for every one of these TG values, we determine the relative porosity corresponding to this specific geometry, assuming that everything that goes above TG is 1, everything that goes below is 0. We calculate the porosity, and then we match the porosity with independent measurement of the porosity using mercury picnometers. So therefore, we have an estimate of porosity, an independent estimate. Therefore, we get this value, and then we stop here. We got the right value of TG, and with this value of the TG, we have a better inference of what is really solid and liquid in the system. So therefore, we can end up from the original to the threshold image, that then it would be used for the analysis. Right. So these are the experimental results. This is one part of the case. So the coffee bed is in the full directions taken into account. Here is the order of 1 centimeter, and then we perform average of the porosity in many different slabs across the direction y. And these are the results for different powder, and you can see that essentially there's nothing very interesting. These are just dry measurement of the coffee powder for different powders. More or less, the profile of the porosity are homogeneous. Nothing special occur. The porosity is of the order of 17%, and that's it. So now we go to the next case where we perform an extraction. And when we perform extraction, things will happen. So we do a classical extraction using a coffee machine with 13 bar, and we compare the CT scan before and after. So these are essentially the two images. This is before extraction, dry. This is wet after extraction. At the top is the inlet, at the bottom is the outlet. The first thing that you see is that it's more black. Okay, so there is more solid after it has been extracted. This is very easy to understand because after extraction you have applied a pressure of 10 bars, so you have consolidated the liquid by hydrodynamic pressure. Okay, and also some swelling might occur. So therefore, swelling plus bed consolidation increase the solid volume concentration, reduce the porosity. And you can see clearly here where in average you go from 70% pre-extraction to a value which is of the order of 5 or 10%. But the most important things that I would like to stress here is that when you look at the porosity profile, if you go toward the outlet, you have an increase of this porosity. So this increased porosity, which means there is more voids in the systems in the outlet than at the inlet. Okay? And this is something that we have observed for many different powders in this extraction process. And also we repeated extraction several times. We look at short after extraction, after a few minutes, after a few hours, one day before. Essentially, we have a very similar pattern. This cannot be explained by the things that we discussed earlier. Fine migration will produce the opposite behavior. Mass will just accumulate there. We increase the solid volume fraction, the porosity will go down. This is not the case. Bed consolidation cannot explain that either, because bed consolidation will consolidate grains more effectively at the bottom of the capsule rather than near the free surface on the top. There are swelling that I'm going to discuss later, and then there is this eventual dispersion, the erosion model that actually was predicted in the previous slides. Okay, so we believe that although this is something that needs to be explored more in detail, we believe that this is a pressure-dependent erosion effect, but it's not something that is related really to a mechanical failure of the particles. the stress that are needed to really break the coffee particle are much, much larger. In fact, you need a grinding machine to do that. Hydrodynamic stresses will not simply break the particle in fragments. What really happens here is that fines, part of the coffee which are already fragmented, might adhere at the largest particle due to electrostatic interaction. And then when you are putting flow, you are essentially recruiting some of the fines which are already fragmented, which adhere at the surface. So therefore, the more pressurized the system is, more consolidated will be the fine. Less pressurized the system here, less consolidated, and it will be easier to remove. So this is one indication, but I think there are many things that need to be explored more in detail. For example, we know that the chemistry of water affects the electrostatic interaction, therefore will produce different erosion patterns, and this is something that we'll need to discuss or to explore more in details. Another thing that you can do when you have this CT data is to take the data, use voxelization, you assign identity to SPH particle 0, 1, and then you run the simulation. This is actually what we could do with SPH. However, we cannot do it in the full coffee bed. It would be way too large. We do it in the smallest cubes of the order of 1 millimeter. And in order to look at the variability of the fact, we repeat these many simulations, many different cubes randomly placed inside the coffee bed with resolution of the order of 10 microns for the SPH particles. And we can extract, for example, the permeability of these beds. So we know the pressure drop, we apply a certain pressure drop, we can measure the flow, we know the viscosity of the liquids, we can infer what the permeability is. So we get the right linear relation, so we get a permeability which is of the order of 5 × 10⁻13. And as you can see here, this is more or less in the order of the permeability for different coffee powder that are observed in experiments. They range between 10⁻12, this is a little bit larger, where other authors predict values that are smaller. And we were somehow in between. One thing from this experiment is that these people, they observed a larger value of the permeability. They were operating a slightly lower Reynolds number. These people here, they operate a slightly higher Reynolds number. And this is actually what we observe. If we increase the flow through these geometries, instead of using a gradient of the pressure of the order of 40 bar per meter, we go up to 400 bar per meter, we increase the flow rate, and what you observe is the permeability actually decrease. So therefore, this finding could, at least qualitatively, reproduce the fact that at low Reynolds number, you have essentially larger permeability than high Reynolds. What is really the reason behind that? Why we have this permeability in the coffee bed, which depends on the pressure drop? We believe that this is due to inertial flow effects. Coffee filtration is a process, is a flow process which occurs at Reynolds 1 or even larger. So therefore, the Darcy law, it's not very accurate in describing this flow. You have to move to the more refined framework using Forkenheimer approximation, introducing inertial effects. And if you use the Forkenheimer, you can reproduce pretty well the change in the slope of the permeability that we have actually observed. This also explains why the permeability, if you assume that you have a Darcy law, why you have this decrease in the permeability, because simply here the slope is 1 and here is smaller. Therefore, when you assume the Darcy law to find the effective permeability, you will get a lower value. And we see that here for different points in the sample and also different powder, we have this different slope between essentially 1 and 2, which is the typical 1 slope corresponding to the linearity between pressure and flow rate for the Darcy law, and here we have the Forkenheimer law, and here we have a Reynolds number of order 1, which determines the transition between the two effects. Okay, so therefore, this is the results that we got. The simulation. Okay, okay, I will skip this. So the take-home message here is that essentially flow inertial effects are important. They can explain pressure drop dependent permeabilities. And the other thing is that inverse porosity profiles are also observed experimentally, and we believe that is related to a pressure dependent erosion, not to mechanical failure, but to a suited to adhere fines to the surface of the coffee particle. Another thing that we have mentioned is the swelling. The swelling will be very important because because water is imbibited. So coffee particles are imbibited with water, and eventually they will stretch. Stretching and will produce swelling, and swelling will alter porosity and will alter flow rates, and therefore we will alter extraction kinetics. So we have in this paper we have introduced a model of the swelling, and following the philosophy of previously that we introduced for the erosion model, we try to introduce swelling at the level of the single SPH particles. We don't have a continuum model, but we act at the level of the single particle. We assume that swelling is related to the amount of water which is imbibited into the solid phase. Okay, so there is no water, there is no swelling. The bigger is the concentration of water, what we call here excess water, or you can call it moisture, for example, some other jargons. So the larger is the water inside the solid, the larger will be the swelling. We propose a model, a simple model of the deformation gradient tensor, which characterize the swelling. Okay? These are the initial position. This is the position after the displacement, after the deformation. And we assume that essentially is proportional to the identity matrix, so the swelling is isotropic. And it depends on 1 over 1 minus C, which means that the larger is the water concentration, the larger will be the swelling. Okay? If C equal to 0, there will be no swelling. If C approach 1, there will be infinite swelling. So if you take this deformation and you map an advection diffusion equation into this domain, which is now having a kind of swelling or ballooning effect, the effective diffusion equation that you have to take into account is slightly modified. You have the classical diffusive terms here, plus there is a terms which take into account the effects of the deforming domain. Okay, so and therefore this is taking account the expansion or on the compression, and J is essentially related to the deformation. So therefore we would like to solve this model with some specific initial environment. So the way we do is inside the coarse, this is the coarse particle modeled by many different SPH particles. They are linked with springs. Okay, they have a kind of equilibrium length. Now this equilibrium length depends on the amount of water which is contained inside the liquid, and therefore we solve analytically this equation, and we end up with expression for the equilibrium length, which depends on the concentration of water in the particle I and particle J. The bigger are the water concentration, the larger will be the stretch of each one of the spring forming this particle, and therefore will produce swelling. This is more or less what happened. This is the concentration of water inside the solid. Okay, this is the surface. This is the center of the coffee particle. At time 0, you have essentially a value here that we prescribe a boundary condition here, and then essentially 0, the particle is dry, and then eventually this water diffuses inside the liquid, and at the same time the size of the particle increases, and we can tune the maximum swelling ratio by simply imposing different boundary conditions here for the swelling equation. For example, if we took Cm equal to 0.2, we have a maximum swelling ratio of 7%, which is really, really small. So if you see 7%, it's really a difference between this particle and this particle. You can see there's almost no difference, but these are the kind of swelling which are reported in coffee particle from experimentalists. They are between 3% up to 10%, not more than this. This is not a huge effect. We will see that already this effect, when you talk about a really packed bed of coffee particle, will produce some alteration in the permeability. Okay, good. So we made some simulation. We take a toy 3D models reproducing the porosity of typical coffee bed. And now we look at the yield. As I say, remember the yield is the mass which actually has been extracted. It's not the concentration that will be the strength. This is the overall mass which has been extracted. You can see that the swelling, here we show results for different degree of swelling, from no swelling to 7%. So if we increase the swelling, essentially the entire volume will expand, the volume of the simulation will expand up to, let's say, 7%. Porosity will decrease. This will produce a decrease in the overall flow rate, because obviously the soil volume fraction increase, the porosity decrease, and also the flow rate will decrease. But the effects for two different clear number, 20 and 40, in the extraction kinetic is not very much. So you can see that the different degree of swelling, for example, if you focus on the continuous line, it's just a minor change in the yield extraction. What really changed the swelling is the strength. You can imagine the strength is much more sensitive to change in the concentration. This is an estimate of the concentration. And here you can see that, for example, if you look at the strength in terms of the brewing time, you see that there is a difference between the blue and the red line. So therefore, there is an increase of the strength in the coffee beverage as an effect of an increased swelling of the particle. This picture has been done at the given brewing time. It's not very fair to show the kinetics of strength in terms of time, because swelling will change the velocity, and therefore essentially mix two effects. Okay, so what people do usually in industry is to show the kinetics in terms of volumes in the cup. So essentially you do your extraction. When you reach at your, let's say, 20-30 milliliter, then you stop the extraction. It's not a measurement of time, it's a measurement of mass. And you can see also in this case, although less than the 30-40% observed here, also in this case you have a 10 or 15% increase in the step. So therefore, swelling by reducing the flow rate and changing the permeability will introduce an effects on the strength. Okay, so I'm just repeating a bit. So I'd like to just very quickly go to the very last few slides, and these are related to a 1D model, because we want to have a more effective model rather than SPH, but more importantly, will be related to the effects of controlling the extraction by pressure drop or by flow control. Okay, this is what I would like to explore. So we have proposed okay, there are many, as you can see, many people have recently proposed 1D models. None of them, however, swelling was explicitly considered. So therefore, we decide to propose another model for the swelling. So the idea of this 1D model is that essentially we couple two dynamics. One dynamic takes place at the level of the bed, and another dynamic takes place at the level of the microstructure, which are the particles. Okay. So therefore, in each of this is the, let's say, the direction of the extraction is discretized by a certain number of layers. In each of these elements, you have one representative particle which represents the coarse, and one representative particle which represents the fines. And we resolve the swelling equation that I showed in the previous slides in these two particle size. Okay. And the boundary condition that we use is essentially that at the surface, these concentrations that we reach there will be equal to the concentration in the bulk divided by a partition parameter. Okay, so therefore this will be coupled with another evolution equation, transport equation for the bulk concentrations that occur at the level of the bed. And in fact, at the level of the bed, we use this equation here. As you can see here, this is pure transport advection. This taking into account the change in the porosity, because if the particles swell more, it will increase or decrease the porosity. And these are two fluxes of mass which come from the coarses and from the fines. So the coarses and the fines will release some concentration of components into the liquids that will be released. The way in which we discretize this equation by finite difference, the only important thing is that we can characterize different powder simply by looking at the typical radius of the fines and the volumetric change of the fine, the radius of the course, and the volumetric change of the courses. And this you can do it very easily when you get the granulometry of different powder. You know already the peaks, so you can know exactly what is RF and RC. They're just the location of the peaks. And in order to know the volumetric fraction of fine and courses, what you do is you just take a threshold and you integrate the distribution function for distance smaller than 10 micrometer. This would be the fraction occupied by fine, and the other area will be the fraction occupied by courses. And with this, essentially this parameter that you obtain here, you can obtain simulation for different powders. Okay, here we go to the last message that we like to transmit, is that if you do an extraction of constant pressure drop, as we see earlier, there are some variations. Swelling has an effect, as you can see, especially in the strength. There is a variation which depends on the degree of swelling. Here we have assumed, for example, just 3%, and if there is no swelling of this 3%, we already have a change in the curves, and also with different powders. Everything is mixed, different powders and different degrees of swelling. There's a lot of variability when you perform extraction at constant pressure. If you impose a constant flow rate, however, you can see that swelling has almost no effect. Okay? And this is, of course, from an engineering point of view, makes sense, because enforcing the pressure is a way to drive the liquid, but you don't know anything about the microstructure, about the effective time-dependent resistance that will be developed within the conflict gate because of fine migration, because of swelling, because of erosion, etc., etc. So controlling the flow rate instead of the pressure drops produce results which are much more, so to say, less dependent on little possibility of variation, which cannot be controlled. We also compare this 1D scheme with experimental data. We are able to reproduce the kinetics for different powders. So this is a tool that actually can be used also in the company to explore different regime of flow parameter. And I would also like to mention that actually this flow control is something that has indeed been exploited just this year by one of the machine from the people that are this called new Illetta machine, which is an Illy machine that actually has been presented in January 2024, and at the moment is just available according to this news in the Italian market. And they have a second valve instead of the first, let's say, pressurized headset. They have a second valve which can control the flow rate in exit. And the way in which they mention this in qualitative terms is that it dispenses coffee in a delicate and progressive manner. That's how flow control is discussed at the level of the news. Okay, so therefore here I go to the summary. The take-home message here is that fines, the small particles, are really important because they can produce time-dependent effects on the permeability, and it also increase the strength because they slow down the flow rate and therefore increase the residence time of liquids near the solids, and therefore they're important for as parameter for increasing the strength of the coffee. Erosion can lead to heterogeneities in the transverse and the normal direction. In the filtration direction, heterogeneity is developed only if you have a model which depends on the absolute value of the pressure. So different pressurization between inlet and outlet will lead to different erosive patterns. We have observed some evidences, although I think to be 100% honest, we should continue to do other experiments also with the swelling to exclude other possibility. But I think that one possible explanation is that the pressure environments affect the adherence of fines to the largest coffee particle, and therefore introduce this pressure-dependent in erosive patterns. Even minor amount of swelling of the order of 3% can alter dramatically the flow rate in a highly packed coffee bed, and therefore produce also again an increase in strength. And finally, when you compare pressure control to flow control, of course, flow control in the end will try to, let's say, rule out all the possible unknown which come from different microstructural effects, therefore controlling essentially the residence time of a liquid at the solid liquid interface, which in the end is the important aspects to promote the transfer of mass. And therefore, here there is some literature on the three different topics that we discussed today. Here there's an acknowledgement to the funding, to the ILI, and also to the national project from the MINECO. And I hope that you have enjoyed this journey into the complexity of coffee extraction, and I hope that the next cup of coffee will be, you will appreciate the next cup of coffee in a more better terms. Thank you very much.
Thank you very much, Mike. I think we'll always get coffee with a greater level of respect from now on. We've got a little bit of time for questions.
Yeah, so you said that they use a pressure-dependent erosion model instead of the typical shear-dependent model. And you said, but it seemed to me that in the shear erosion model, there is more channeling than in the other one. Do you know why? At least in one of the pictures that you showed, it seemed to me that there were more channels when you used the shear erosion model.
I think that the shear erosion, its explanation, of course, is that there is a positive feedback mechanism between this random small channel that might occur in the porous media. A small channel, we have less flow rate, the stress will be smaller, the flow will go to the larger, and therefore it will increase the velocity and the stress. So on the Y, it will be probably that the fact that you erode also the bottom part, it might increase the overall velocity. In this case, for example, phi goes to zero, and therefore essentially it produces a large velocity over the entire transverse direction. This could act as a kind of homogenization, perhaps, but
I don't quite understand how you obtain the permeability of the fines. So most of the resistance increase comes from these fines accumulating in this layer, right? And what I understood was each fine is fixed at a certain point, and it just adds to the resistance through the Stokes law.
In the first part of the model, we have a model the resistance of the fines by fixing them in space, and therefore with a flow going through certain portion of fines, yes, will increase.
So basically, I remove a fine and it reaches a point. I decide it's the end of its
stop there, and then
it just keeps adding to the resistance because it's a Stokes law.
It increase the resistance as long as they accumulate more. The resistance will increase. Yeah.
Okay. But isn't there a lot of play, because if I pack them more closely together, the space available will be less, and that's very sensitive to. The permeability should be very sensitive to the packing when you're forming the filter. So how do you make that robust?
Yeah, there are two things. One thing that I discussed at the beginning is one model to reproduce the time-dependent effects. Time-dependent effects are due to fine migration, and then eventually we are saying, okay, good. When they migrate, they do not offer any resistance because they are in a kind of free flow. And when they are stacked, they will produce a resistance which is increased. In the second part, when we will try to repeat the simulation with from the microCT data, we are not considering moving fines there. We are just taking snapshots of the solid phase, and we are looking at resistance, flow rate, and permeability. So if you are interested in time-dependent effects, you have to use the
Yes, that's the first one. I was thinking of the first one.
Yeah.
And I was thinking, okay, if I pack them, if I decide to stop them more closely packed, I'm going to have a much less permeable layer than if I just stop them anywhere. I mean,
I think that
in reality, it depends. That's what I'm trying to say. It depends on how closely packed you have them.
completely. I mean, in the simulation, there was a kind of toy 2D model that has no pretensions to reproduce realistically. It was just a mechanism to show that the migration, if there is migration, can produce a relaxation process will take place on typical time scale. The fines typical time scale that the fine need to go from one part of the complicated to the other part of it. That time scale can be measured. However, it is true. I mean, depending on how packed is the coffee bed, there could be clogging, there could be fines that are just stopped somewhere in the bath, that did not even reach the filter. And this will alter, so to say, in quantitative terms, these relaxation times. But the essence is the migration.
Marco, thank you very much for the presentation and showing some of the data-driven research. I really appreciate it. I have two questions. One very technical, but to really understand. When you study the migration of fines, you use SPH, and I understand that everything is saturated, so it's already full of water, and you have the big particles and the small fines. Is that correct?
Yes.
Now, you probably, the question is, are you using a unique SPH mesh or points or particles, or do you have different ratios, different ranges for the water than for the coarse mesh? The radius, the number of particles, is it unique?
The number of particles is homogeneous and unique. We don't have any adaptation or different resolution.
And therefore, you have some of them, the coarse ones, which are fixed in the domain.
Yes.
The fines which can move. Do they actually move, or you find where they were and now you put them, you paint them with a color and you move the colors? We randomly select initially SPH particles and we target them as a fine. At that point, they are just SPH particles, passive tracers, nothing more. There is no physics there, except the transport of some material through a specific configuration. Same density as the fluid, or you change the density?
Well, no, it's the same density, but the density has no, because this is a highly
high pressurized system.
Yeah. Also, there is no diffusion because you can estimate the typical Becquerel number exceeds 100. So there is no even.
And you solve it with other stoves. Now,
so,
my second question, which is the one I want.
Yes.
What happens? How big is the error if instead of using Navier stoves, you use Darcy? Which will make your life easier. And probably larger errors, but I wonder how large could be those errors.
So the way the point where we checked the Darcy was in the.
Yeah, but I know you have been using Darcy and you have been modifying the parameter. My question is, if instead of using Navier stoves to solve the flow motion, if you would use Darcy flow, which is linear, would that make a big difference in how those fines move along the fluid?
Okay, we didn't check that to some extent. The only things that I can say is that the manuscript that we use are at final granular.
Yeah.
So therefore, this should introduce some difference.
Yeah.
This could introduce some difference.
Because as far as 12.
Yes, so it could be also 20. But of course, no one really knows. I mean, people know what the people know is the volumetric flow rate from which they can infer the superficial velocity, and that's it, that's all what you can know. What's really happening inside, what kind of channeling are open, and what is the local value of the velocity, and all these sort of things that remain a mystery, I think, the best of my knowledge.
Great presentation, and great problem. Thank you. Thank you very much.
Any final questions? No? Okay, well, let's thank again, Marco, for the fantastic.